Hello, everybody. My name is Jose Jimenez, and today I'm going to present the study Identification of Potential New Inhibitors of Mycobacterium tuberculosis, the hydrofolate reductase, using an in silico approach. Nowadays, tuberculosis is a disease that still causes havoc and is one of the leading causes of death worldwide. According to the World Health Organization, Peru is included in the list of high burden countries for multi drug resistant tuberculosis. As an example, here in this bar chart, we can see that between 2008 and 2015, the number of cases reported for multi-drug resistant tuberculosis has increased. As we can see, the emergence of these strains is generating a lot of trouble in Peru. Also, comorbidities with diseases like diabetes or AIDS have been detected, the application of inappropriate tuberculosis treatment regimens, and finally, the COVID 19 pandemic has worsened the situation since health centers were not available for the rapid diagnosis and treatment of this disease. With the emergence of multi-drug resistant strains, it is crucial to have new alternatives of treatment. Hence, we need to find suitable drug targets. In this case, we propose the enzyme the hydrofolate reductase from Mycobacterium tuberculosis. This enzyme is important for bacterial survival as it catalyzes the reduction of the hydrofolic acid to tetrahydrofolic acid using NADPH as a cofactor, being essential for nucleic acid synthesis. Another aspect to consider is that a sequence similarity of approximately 26% has been found between this enzyme and the human reductase. This provides an opportunity to discover drugs that specifically target the bacterial enzyme. Furthermore, a study published has found that this protein is also a target for isoniazid, which is a widely used drug against tuberculosis. And here we have as examples some studies where interactions between this enzyme and some inhibitory compounds have been evaluated using in silico methods. Now, why did we need to use an in silico approach? Processes such as virtual screening or molecular docking allow the identification of potential drug candidates in a cost-effective way without the need of resources commonly used in vitro and in vivo experiments. Currently, there are large-scale datasets that enable drug discovery. In addition, these computational methods could be useful at early stages in drug development. Finally, there is a structure-based approach, which is used when the 3D structure of a target is available, and this protein is more direct, rapid, and efficient in identifying lead candidates. Based on the aspects mentioned before, the aim of this study was to identify inhibitory compounds that could bind with high affinity to this enzyme, the hydrofolate reductase, and could form stable complex systems. For that purpose, we used this 3D protein structure, which was obtained from the RCSB protein data bank with entry ID 6NNE. This structure represents a crystal complex formed between this enzyme and diaveridine. Now let's talk more about diaveridine, which is a non-antitubercular drug. We can see in its 2D structure that this compound has a 2,4-diaminopyrimidine group. We found in some articles that this group was used to create some derivatives whose structure resemble the native substrate of this enzyme, such as folic acids. Also, this chemical group has been used before for the synthesis and characterization of various compounds, such as trimethoprim, and these compounds or derivatives are known as non-classical antifolates. Now, I will explain the methodology used in this study. First, for compound screening, we use this web server called Pharmit, which allows us to perform a screening based on pharmacophores. In this case, we use all pharmacophore features from this 2,4-diaminopyrimidine group. We use a maximum score of -8 kilocalories per mole and a maximum value of RMSD of 2. Then we obtained an initial library of 314 compounds from Campbell, Coconut, and Zinc databases. Then we performed the filtering in this program, Data Warrior, based on physicochemical properties considered in the Lipinski rule of 5, molecular weight no more than 500 Daltons, number of hydrogen bond acceptors and donors no more than 10 and 5 respectively, and a log P or lipophilicity value less than 5. Also, we consider a log S or solubility value no more than -5, and we use included compounds with no stereocenter. Also, we excluded some those compounds that were mutagenic, tumorigenic, and caused irritating and reproductive effects. Next, we did a virtual screening using first the 22 compounds obtained from the filtering. An energy minimization process was done to each of these compounds using the software Pirx. We did the same with the protein structure, which was minimized with the Yasara server. And then all of these structures were used for virtual screening in this program, EasyDocVina. Here we have the box center and dimensions considered, and from that process, we selected the best 8 compounds. Then we perform a molecular docking with this tool, AMDoc, using the same box center and dimensions. And from these 8 compounds, the 3 best were selected for visualization and interaction analysis using BioVia Discovery Studio and PyMol. After that, we did molecular dynamic simulations using the Linux distribution, Ubuntu, and GrowMax software. We used a Charm 36 port field. Simulations of 10 nanoseconds were performed, and we did RMSD analysis in Qt Grace to assess conformational stability. Finally, we evaluated the properties and drug likeness with 2 servers, SwissAdme and AdmeSAR 2.0, which were used to predict lipophilicity and water solubility, gastrointestinal absorption, blood-brain barrier permeability. We evaluated if these compounds were P-glycoprotein substrates and inhibitors, cytochrome inhibitors, and their drug likeness according to the rules proposed by Lipinski, Weaver, and Muji. Cacos 2 cell permeability, their toxicity as Ames mutagenesis, carcinogenesis, inhibitor of human hair channel, hepatotoxicity, acute toxicity, and nephrotoxicity. First, we have the virtual screening results. Here we see the information of the best 8 compounds selected, the compound number, ID, and binding energies in kilocalories per mole. Those 8 compounds were obtained from Campbell and Zinc databases, and their binding energy values are less than -9, which indicates high affinity towards the enzyme. Then we have the molecular docking results. We see that only compounds 2, 3, and 4 have higher affinity towards the enzyme compared to diaveridine, whose energy value is more positive. Also, if we evaluate inhibitory constant, we can see that the value for diaveridine is almost 12 micromolar. However, for compounds 2, 3, and 4, their values are in nanomolar, which would indicate a more potent effect as a smaller amount of medication is needed. Besides, when comparing all compounds, compound 3 has the best values. Now we have the analysis of interactions between the enzyme and diaberidine compounds 2, 3, and 4. To sum up this part, we see the hydrogen bonds, p-alkyl and alkyl bonds, were shown as the most predominant non-covalent interactions that could have contributed to their affinity. However, we can see that some unfavorable interactions were detected in diaveridine and compound 2, which could have had an impact on their binding energy values. Another important aspect to consider is that there were common amino acid residues that interacted with all compounds. These were isoleucine 5, alanine 7, and aspartic acid in position 27. And it appears to be that the pharmacophore features of this chemical group, 2,4-diaminopyrimidine, that were used tend to be more crucial for interactions with these residues. Here we have some articles that support what was said before. For example, molecular docking using rigid receptors can cause atomic clashes between the receptor and ligands, which were shown as unfavorable interactions. These 2 articles have information about interactions between the bacterial enzyme and some compounds with 2,4-diaminopyrimidine groups, mentioning some amino acids such as isoleucine 5, isoleucine 94, aspartic acid 27, and here this article mentions that there were strong interactions between this chemical group and 4 residues, including isoleucine 5, tryptophan 6, isoleucine 7, and phenylalanine 31. With respect to molecular dynamics, we can see that complex systems with compound 2 and 4 were the most stable. Their average RMSD values are lower than 0.35 nanometers. In the complex form with compound 3, we see that there's a significantly increase in RMSD values from 8 to 10 nanoseconds, which indicates conformational instability. Based on those results, compound 2 and 4 were selected for ADMET and drug likeness predictions. Now, regarding ADMET properties, we can see that both compounds um, have positive values of log P, which represents that these are lipophilic. Log S values between -4 and -2, which indicates water solubility. They also have high gastrointestinal absorption and cacosoil permeability. These properties are ideal for drugs that will be orally administered. In addition to that, these compounds are P-glycoprotein substrates and are not inhibitors. This information is crucial because the administration of these compounds with drugs that induce glycoprotein production will be less bioavailable. Also, we see that compound 2 inhibits more cytochromes than compound 4. This is important and should be considered when administering drugs that are metabolized by those cytochromes. And considering toxicity prediction, compound 2 and 4 were predicted to be positive for Ames metagenesis, and both would be hepatotoxic. This scenario provides an opportunity for in silico lead optimization to make compound 2 and 4 less toxic, and these new derivatives could be further evaluated. And finally, both of them satisfy the drug likeness parameters according to the rules proposed by Lipinski, Weaver, and Muji. To conclude this presentation, from an initial library of 340 compounds, two of them, compound 2 and 4, had a high affinity towards Mycobacterium tuberculosis, the hydrofolate reductase, and they together form stable complexes. Both compounds had optimal physicochemical properties and satisfied the parameters for drug likeness. Also, both compounds were predicted to be mutagenic and hepatotoxic. However, this provides an opportunity for optimization of their structures so that they will be less toxic. And finally, their inhibitory potential can be further assessed using in vitro and in vivo models. We have some references using these slides, and thank you very much for your attention.